Good morning, students. This is Nagesh Patil, Department of Chemistry, Virishav College, Bellary. So I am going to take a class on organometallic chemistry for MSc second semester students. Then how we are going to define organometallic compounds? The name itself indicates where a metal has been bonded to organic ligand through a carbon atom. So such type of compounds we can call it as organometallic compounds or organometallic complexes. So that how we are going to define a definition for organometallic compounds means a compound formed between a metal and organic compound containing metal carbon bond are called organometallic compound. So that indicate an organometallic complex must contain at least one metal carbon bond. So the ligand it may be a CO, NO, N2 or H2, but it is very important such that it doesn't include a cyanide ligand. So it is coming under a classical coordination chemistry ligand. So one of the important characteristic property of organometallic compound here, that is it contains two types of bond. So one is the sigma as well as the pi bond between a metal and then carbon of organic ligand. So look at by history, that is this all synthesized in 1827 only, but the structure not full known until in 1975 due to the typical type of bonding between a metal and the carbon like sigma as well as the pi bond. So in later, so next carbonyl compounds has been synthesized in 1890. Then the other reagents like Grignard reagent has synthesized in 1900. So there are many compounds come across so early of the 19th century. So then that the classifications of the organometallic compounds. So the first comes ionic organometallic compounds. So the name itself indicating that is ionic organometallic compound, that indicates a metal consists a more ionic in nature. So that most of the organometallic compounds of alkali metals except lithium fall in this category. Such compounds are colorless and they are solid in nature, and it is very important such that they are soluble in polar solvent due to the presence of ionic character. So the next type of classification, the compound containing metal carbon sigma bond. So here the metal of group 2, 13, 14 and then 15 of the periodic table, and some of the transition metals with fully filled d orbital such as zinc, cadmium and then mercury fall in this type of classification, and they forms sigma bond between a metal and the carbon of organic ligand. So then comes ylides. So these are the type of compound where in which a metal is doubly bonded with the carbon atom of the ligand. Such compounds are formed by the main group elements as well as the transition elements. So next comes organometallic compounds with multi-centered bond. The name itself suggesting that a metal has been bonded to various number of ligands. So that is coming under organometallic compounds with multi-centered bond. Then organometallic compounds with pi bonding. So it is important category, includes organometallic compounds of alkenes, alkynes and some of the carbon-carbon containing compound having electrons in their pi molecular orbital. So it will overlap of this pi molecular orbital with vacant orbital of the metal atom give rise to an arrangement in which a metal atom get bonded to all the carbon atoms. So the best example for organometallic compound with pi bonding ligands like ferrocene. So then the naming of the complexes. So the same rules govern for the coordination chemistry what we are following the rules. So the same rules will be governed for the organometallic compounds also. So first ligands named before central metal atom, then anionic ligands ends with O, and some of the neutral ligands like water is should named as aqua, amine, NH3, then CO as a carbonyl. So if it ligand in complex used to make a prefixes, if the ligand is 2 or more then it should be di, if it is 2 then 3 as a tri, tetra for 4, penta for 5, then hexa for 6. If the ligand is complex, then we should use as a BIS for 2 ligands. If it is 2 ligands, it is in a complex ligand, then we should call it as a BIS for 2, TRIS for 3, TTRAKS for 4. So it is the naming of an organometallic compounds as usually what you have studied in the last classes. Then some of the ligands what we are using in the organometallic compounds, the first one is carbonyl, very important ligand. Then carbene, carbine, cyclopropenyl, cyclobutadiene, cyclopentadienyl, benzene, 1,5-cyclooctadiene, ethylene, acetylene, allyl, alkyl, and then acyl. So these are all the ligands which are coming across organometallic compounds. Then next word we will use in organometallic compound as a hapticity. So hapticity indicates a number of carbon atom attached to the metal ion. So that indicates hapticity. So they have given the neutral, that is eta 1. So eta means how many number of carbon atoms. So in cyclopentadienyl totally 5 carbon atoms are there. If out of 5 carbon atoms only 1 carbon atom has been bonded to metal ion, so such type of compounds we can call it as a monoheptacyclopentadienyl. If it is 3, that is eta 3 indicates only 3 carbon atom out of 5 carbon atom has been bonded to central metal ion. Then eta 5 indicates all the 5 carbon atoms has been bonded to central metal ion. So that is called as hapticity. So that is number of carbon atoms bonded to metal ion. Then 18 electron rule, or also called it as a inert gas rule. So this will give you idea about the stability of the complexes. So the octet rule governs organic and then simple ionic compounds. So we will say it as a octet rule to decide the stability of the organic as well as the simple ionic compounds. So we will count the number of electrons in the s as well as in the 3p orbital. If it is 8 electrons, then we can call it as a stable for organic and then simple ionic compounds. But for organometallic compounds, so we will call it as a 18 electron rule, because in valency shell, so the 3 orbitals are there. One is s, 3p and then 3d. If all the orbitals containing 18 electrons, so that indicates they are very stable in nature. So that phenomenon is called as inert gas rule or 18 electron rule. So the number of electrons donated by the ligand and the number of electrons present in the valency shell of the metal ion, so that will give about the stability of the complexes. So we have two methods for the counting of electron in the valency shell. One is ionic method and one is neutral method. So method A we will followed by ionic method, and then method B, that is neutral method. So just it will vary number of electrons donated by the ligand here. So if you are going to calculate the 18 electron rule with the help of an ionic method, means then you should know how many number of electrons donated by the ligand. So example here is hydrogen, so it will show some negative charge, so that indicates it will donate 2 electrons. Then by the neutral method it will donate 1 electron. So likewise, so various ligands are there, then you should know number of electrons donated by the ligand for ionic as well as the neutral method. So here also they will given some of the number of electrons donated by ionic method as well as the neutral method. Then the example we can carry out for to count the electron rule for the organometallic compounds. So the first example is carbonyl compounds. Then we can know total charge on the ligand is 0, it is a neutral ligand, so it is 0. So the charge on chromium 0, that indicates the oxidation state. Then chromium number of electron is 6, then number of ligands are 6, one ligand will donate 2 electrons, totally 6 ligands are there, 12 plus 6, 18, so it will show a stability. So next one also same, so the total charge on the ligand, so that indicates if it is having any type of negative ligands are there. So 2 charge, so one is chloro and then cyclopentadienyl, then the oxidation state will become +2, then 6. So we are calculating in the form of an ionic method here, then you should know the number of electrons donated by the ligand and the charge of it. So then the electrons donated by the cyclopentadienyl is 6, then carbonyl is 4, then chloride 2, totally 12 electrons, then the number of electrons present in the metal ion 6, totally 18. So once again, next compound, so total charge on the ligand is 0 because the carbon it is a neutral ligand. Then metal ion shows some positive charge, so number of electrons is 6 now, then 6, and the number of electrons donated by the ligand 12, totally 18. So one more conjoint here, so that if it is a polynuclear complex, so the 1 electron will be contributed by the metal-metal bonding, so Mn1. So total charge on the ligand 0, so Mn 7 electrons, so 5 ligands are there for M1M. So it will contribute 10 electrons, 10 plus 7, 17, and the 1 electrons you have to calculate for metal-metal bonding. So once again there is an exception for the 18 electron rule. So the number of electrons are not 18, but they are stable in some of the complexes. So that is a violating of 18 electron rule, or nothing but 16 electron rule. So this is due to the all high spin d8 metal ions are octahedral, but the low spin d8 metal ions are square planar. So important class of square planar low spin d8 metal ions are like rhodium, iridium, nickel, palladium, and then platinum. So they will show low spin complex with the structure of a square planar, so they will not showing 18 electron. So they are violating the electric electron, but they are stable in 16 electron rule. So first you can go for it. So in the first example they have shown that is a platinum in +2 oxidation state. So then the number of electrons are 8. Then chloride 2 electrons, 3 into 2 6. Then ethene 2, totally 16 electrons. So it is stable in 16 electron rule. So then platinum also +2 oxidation state. The number of electrons are 8. Then chloride 4 are there. 4 into 2 8. 18 plus 8 16. Then iridium oxidation state is 1. Number of electrons in iridium 8. Number of electrons divided by the chloride 2, then 4 to totally 16 electrons. So this is on 18 electron rule and then 16 electron rule.